Okay, with this video, we're going to take a look at experiment number 4. And let me share my screen with you. Go over here and grab the circuit maker. Okay, so what you see here is you see the circuit, which is a resistor 1.2 k ohms in series with a 0.1 microfarad capacitor. And it appears to be driven by a -1 to +1 or 2 volt peak to peak 1 kilohertz sine wave generator. However, I've set this up as a Bodie plot, and it turns out that signal generator is just there as a placeholder. And what actually happens is the circuit has a voltage applied to it where that swings from or sweeps from a low frequency up to a high frequency, whatever I set up in the simulation analysis panel. So we know the resistor here is going to be 1.2 k ohms regardless of the frequency, whereas this guy here, the capacitor, 0.1 microfarads, will have a reactance to the input signal, and that reactance is dependent upon a frequency. As a matter of fact, the reactance of a capacitor is given by 1 over 2 pi fc. So as the frequency is low, say 0 hertz or DC, that reactance will blow up to infinity. If the frequency gets very high, in the hundreds of megahertz range, it turns out that now that reactance goes towards 0. And the limit as frequency goes to infinity, the reactance would be 0. So the series circuit uses, standard circuit parameters or how we deal with circuits when we try to solve them. It's a voltage divider. So it turns out that, I have a 1.2 k ohm resistor here. When the capacitance, reactance to the capacitance is very large, close to infinity, this will actually, the vast majority of the output will occur across this capacitor, or you might even consider this an open circuit, and whatever you apply will appear in the output. When the frequency goes up and the capacitor looks more and more like a short circuit, obviously less and less will appear on the output. You can actually come up with equations to figure out exactly what's going on. The other thing here we should talk about is the fact that when I have resistance and reactance in a circuit, I get impedance. The combination of those two things, resistance and reactance, is impedance. And it turns out that if we use Ohm's law with impedance, the series circuit here will be the reactance of this capacitor divided by the impedance of these two elements combined together. So what I'll do now is I'll take and hit the running man here and actually simulate the circuit. What you see is we don't need the multimeter, get rid of that guy. What you see here is we're going to look at point A, which is across the capacitor to ground. We have an oscilloscope display, and we have this display down here, Bodie plot. I'll activate the Bodie plot, and you might see the banner gets a little bit darker here. And I'm going to blow this guy up. So what happens is you take a look at the bottom scale, 1 to 1 megahertz. That's a vast range in frequency, and it's set up basically as a linear scale right now with 500 kilohertz in the center. I'm going to take and change that, go up here, and I'm going to change the y-axis to, the x-axis rather, this way, to a log scale. And let's just hit OK. And now you can see, well, boy, that really changes what we see for that display. Now we start at 1 hertz, 10 hertz, 100 hertz, 1 kilohertz, 10 kilohertz, 100 kilohertz, and finally 1 meg across the bottom of the y-axis. So the center now is 1 kilohertz as opposed to 500 kilohertz like it was before. And you can see that at low frequencies, it looks like most of the input arrives at the output, as we mentioned before. Then we get the high frequencies and very little makes it to the output. One thing we might do, one more thing, is we tend as electrical engineers to like to do this. Let's make the y-axis decibels. And when I click on this, we get a nice curve here, which is the classic legacy Bodie plot, where frequency is down the bottom here, the y-axis, and it's logarithmic, and the output is listed across as the y-axis here. Get them right, hopefully. And it's in decibels, which is logarithmic also. So what we discover is someplace around, well, between 1 and 2 kilohertz, we start to have this drop off. That's probably where our cutoff frequency will be. And then we have a very linear drop off where we can calculate that number of dB per decade rather, or number of dB per octave. So one last thing I can show you here is, let's go over to this and let's take and watch phase degrees here. So hit OK, and let's take and make the x-axis. Let's see, we made the x-axis logarithmic. Let's make it linear, I guess. Let's see what happens here. No, that's not good. We've squashed the frequency up. Again, we'll make it logarithmic. Phase in degrees. I guess that's about as good as I'm going to do here. So hit OK. And what we discover here, it starts at 0 and heads down towards minus 90 degrees. Now, for a capacitor, the current will lead the voltage. That is, I can close a switch and the amount of current that flows in the external circuit to the capacitor will be instantaneous at some value. The voltage across the capacitor, however, it takes time for it to take and rise. So what happens here is, with this logarithmic plot, I don't look like it too much here, but I guess the problem is the number of points I've chosen to plot. It tends to look like it's not very smooth. It goes through about 45 degrees, somewhere in here, which is between 1 and 2 kilohertz again. So that's the cutoff frequency, as well as at minus 45 degrees is when the resistance of the 1.2 k ohm is equal to the reactance of the capacitor. I'll get a 45-degree phase shift. So that's basically what we're looking at. And again, let's take a look. Let's go back to setting this here to the decibels for the output amplitude. Hit OK, and we see this plot here. Notice it hasn't gone down to 0 on megahertz. The other thing I can do real fast is go over here and move C down, and C, when C is about 3, which I can't quite get it on. A is right about here, and that happens at about, let's see, 1.28 kilohertz, it looks like. If I blow that up, let's move it over here. Whoops, and again, it's tough to move A around here because it turns out that A is, it's the number of points that I tell the simulation to plot. Oops, I go back the opposite way. I think it's right about there. And that's about 1.328 kilohertz for the cutoff frequency, where the output goes down by 3 dB. Now, by the way, I should be more accurate with my 3 dB. I don't think I'm going to be able to get, well, no, I guess I can go to 2.993. And what happens here? So right about there. So maybe even more accurate is 1.297 kilohertz for the cutoff frequency. Anyway, that's what Circuit Maker can show you for, let's do one last thing. Let's go to phase in degrees. Let's see what happens here. We discover that back here we are right here, and if I bring C down, which should tell me the phase. Well, you see that we're just about the same place on the dial. That's about 45, and I go and I, oops, nowhere to go. It's gone. If I go, this thing moves very rapidly now. So let's see if I can get on it again. I don't know. We'll go and we play with it. Looks like right about there again. 1.312 kilohertz. So they're very close. Nope, then if I go looking, it's already jogged over a little bit. 1.328 kilohertz for where the phase angle is 45 degrees, roughly 45. So again, Circuit Maker can show you, I'll click back here, can show you quite a few things about a circuit in the Bodie plot mode. This would be called the low pass filter, by the way, because most of the low frequencies are left through and the higher frequencies are attenuated.